Well, what we've been doing up to this point is just taking all the information we've gotten from the word problems and forming those inequalities and then forming that one equation. Whatever they asked us to maximize or minimize is what we're making the actual equation. So if we're maximizing profit or minimizing cost or we're maximizing our rate of return or our interest, okay? Those are what we've been doing so far. And now what this is going to do, what this steps right here, is we're going to take it from here and we're actually going to find our true answers. What is the maximum value in order to maximize our profits? What do we have to do? How do we have to split that money up? Is it 10,000 here, 12,000 there, and 15 there? Or, that kind of thing. Or if we want to minimize costs, then we only need, look at that reservoir problem and the amount of water coming from the reservoir or coming from the pipeline. We only want then a total of 5 million coming from the reservoir, but 12 coming from the pipeline. And that's what we need to find out. And how we're going to do this is now taking it to the steps of graphing it. And step one, as usual, is what we've been practicing. We want to graph our inequalities. I made a little note here that you might want to pay attention to. It's going to be helpful to graph with respect to our X and Y intercepts. Because remember, all of these word problems that we've been doing so far, we've actually been graphing them all in, let's say we've been talking about doing it in quadrant 1 because all the X's and Y's and sometimes the Z's all had to be positive. So really what we're doing is we're talking about looking at this in quadrant 1, and we want to know when it enters quadrant 1 and when it exits, therefore the intercepts. Okay, so keep that in mind. Instead of doing y equals mx plus b this time, we're actually going to be graphing using our intercepts. And we're going to be doing mainly that with word problems. Okay. And then number 2 is we want to find the specific area where all the shading overlaps is where our potential solutions are going to come from. And what we want to is in that overlapped and shaded region, we specifically need the corners. So what we're going to have to do is find corner points where two lines intersect each other. And we technically know how to find where two lines intersect. We have the substitution method, the elimination method, and the matrixing method. So we can definitely find out where two lines intersect. And then thirdly, we want to find the values of each corner point. Like we said, we're going to find that through the intersections. And then we're going to plug each corner point into the equation. This is the only area where we're ever going to use the equation. We're not going to graph the equation. We're only going to graph the inequalities. But where we're going to use the equation that's what we're going to plug all of our corner points into. And the largest value that comes out of the equation is the maximum value. The smallest value that comes out of the equation is the minimum value, so depending on what the problem says. And I have a little special note, is that in your shaded region, if it's bounded, then there's for sure a max and a min value. However, if it's not bounded, so if that shade can go on forever and eternity, then obviously we won't have a maximum value. Okay, let's start out small. Let's just look here at example 6. And we want to find the maximum minimum values for this specific equation, just z equals 3x minus y. So what would normally have happened is we would have had all these inequalities. It looks like probably 4 inequalities, and you would have graphed them. Let's say if I finish this out, there would have been a line coming down through here, one coming through here, another one coming down there. And what's going on is all the shading, when you overlapped all the shading, it's producing this region right here. So it looks like the shading would have been below that line. It would have been to the left of that line, above this low line, and then to the right of this vertical line. And that creates a shaded region. After you found that shaded region, you really have to know these corner points. So of your corner points, I put CP for corner points. They are 7, 9, 10, 1, 2, 2, and 2, 6. Okay, so after you've graphed and found your shaded region, next thing you have to do is find your corner points. In this case, they were given to us. And then after you get your corner points, what we do is we go back to our equation and we plug our corner points into the equation. So 3 times that x value minus the y value. And it'll come back. So 3 times the x minus the y. 3 times the x minus the y, and lastly. Okay, so let's evaluate this. So 3 times 7 is 21, minus 9 is 12. 3 times 0 minus 1 is negative 1. Let's see, 6 minus 2 is 4, and 6 minus 6 is 0. All right, in this problem right here, it wants us to find the maximum value and the minimum values. Well, the maximum value is going to be simple. It comes from the highest value once you plug it in. So right here, 12 is the largest, so it's the max. So we're going to have a max at the point 7, 9. The minimum is obviously the smallest one, so negative 1. So we're going to have the minimum value at the coordinate 10, 1. And that answers the problem right there. It's bounded, so it has a max and a min. And let's say this was a word problem. Then what we would have said is, let's say, X was, the number of t-shirts sold, and Y was the number of hats sold. Well, then to maximize your profits, you want to sell 7 t-shirts and 9 hats. To minimize your profit, then you would sell 10 hats and 1 shirt or something. You know, that's what we're looking at when we're interpreting this problem. So let's go to the next one. Let's look at example 7. Here with this example, it looks like we had several lines come in and made quite an interesting solution region. One came down like that. There's probably another line that shot down like that, and there was a third one that came down like that. But in each case, we've all been graphing here in quadrant 1. So right away I knew that like one of the inequalities was x is greater than or equal to 0 and y was greater than or equal to 0. So you see how this all curves and it keeps everything here up here in quadrant 1? It's a good thing to look at. And we're always graphing kind of above these, but anyways, there's an overlap of a shading region, and what it did was create these corner points, specifically 0, 7, 1, 5, 4, 2, and 8, 0. Okay. So what we're going to do is we're going to go back and plug these up into our actual equation to figure out max and mins. So z is going to equal 7 times my x value plus 9 times my y. So 7 times x and 9 times y. And lastly, 7 times x and 9 times y. So evaluating this all this out, 9 times 7 is 63. 7 plus 45 would be 52. 28 and 18 give us a value of 46, and 7 times 8 is 56. Alright, so we would normally go up there and say, okay, let's find our max and let's find our min. Well, our minimum value would come from the smallest one listed up there, and that looks like 52. So we're going to get a minimum value at the point 1, 5. Now max, this is where you got to take 2 seconds though. The max you would think it would be 63, but it's not. So if we go back to our graph, it's unbounded. We don't know. There could be potentially another higher corner point somewhere out there we just don't know about. So the max, what we're going to say is there is none, because this is unbounded. So we just have to watch out for it. If it's bounded, I can put a circle around it, kind of like in this last example. Let me go up there. Because I can actually circle it. This is bounded, so there has to be a max and a min. But if it's unbounded, I have a min for sure. I potentially don't have a max. So we have to check for that. Okay? All right, let's go to example number 8.